Okay, so for this lesson, which is called the electric potential and potential energy, we have the following. So let's say that we have two plates. One of them is positive plate and the other is a negative plate. So we know that field lines, they exit from the positive plate and they enter the negative plate. Now this is what we call as uniform field, which means the following. Wherever you go between the two plates, you have the same value of electric field. So let's say that we have a charge, a positive charge, which is moving in the same direction as electric field. So it moved a distance of d, let's call it as dx, for example, this is ex. So it moves this distance in the electric field. As it is moving, it's being attracted to the negative plate, which means that its speed will increase as it is moving. Which means the following: as speed increases, kinetic energy increases, and therefore the potential energy of that particle will decrease. So we can say that change in potential energy for this will be minus the magnitude of the charge multiplied by the electric field, which is on the x-axis, multiplied by the distance or displacement, which is on the x-axis. This is what we call as change in potential energy. So this is change in potential energy. One thing you should keep in mind that we want the electric field and the displacement to be on the same axis. So if I had electric field on x, I take displacement on x. If I had electric field on y, I take displacement on y, and so on. So I'll give you all the cases now for positive and negative charges. So if I had electric field like this, and we had a positive particle moving in the same direction of field, then the change in potential energy of a positive particle will be decreasing as it is moving, will be negative, so we can say. So change in potential energy will be negative. It means that it will lose potential energy. And if the same charge, which is the positive, was moving opposite to the electric field, then the change in its potential energy will be positive, since it would be slowing down as it's going to the positive plate. If it's going to the positive plate, positive and positive repel, therefore it will slow it down as it moves. For the negative particle, it's the exact opposite. So in the same direction as electric field, it means that we will have a negative charge going to the negative plate in that case. So negative going to negative, it means that the potential energy will be increasing, or the change in potential energy will be positive. And if it was going opposite to the field, it means that it is going to the positive plate. It means that the change in potential energy will be negative, since negative is attracted to positive, so it will be losing potential energy and gaining kinetic. Or simply you can think of it like this: a charge in its normal motion will lose potential energy and gain kinetic energy. We have another variable which we call the change in potential or potential difference, which we call as delta V. So delta V, which is equal to delta PE change in potential energy over charge. Or we can calculate it using another formula, which is the following. So delta V is equal to minus ED. Okay, so let's do question 3. So in question 3, it's saying the following: A uniform field with a magnitude of 250 newtons per coulomb is directed in the positive x direction. So electric field here is on the x-axis, so we call it as Ex, and it is equal to 250 newtons per coulomb, and it's directed to the right. A 12 microcoulomb charge, so Q here is given as 12 microcoulombs, so 12 times 10 power minus 6 coulombs, moves from origin to the point of 2050, so 20 centimeters and 50, which is, we can rewrite it as 0.2 and 0.5. Now which one we're going to take? Keep in mind that in coordinates the first one is always x, the second one is always y. So we take the x displacement since we have electric field on x, so we say that dx is equal to 0.2 meters. Then we say that they want us to calculate the change in electric potential energy as a result of position for this charge, so we say that delta PE. Why did I use this? So because they said that they want the change in potential energy and not potential only. If it was only potential, then it is delta V. So delta PE is equal to the following. It is equal to minus Q times E times displacement, which is equal to minus 12 times 10 power minus 6 multiplied by electric field, which is 250, and multiplied by the displacement, which is 0.2. Displacement here is in the same direction of field, since the field is to the positive x-axis, so we put it as positive displacement. If it was opposite to the electric field, we put it as negative displacement, which will give us the following. It would be minus 6 times 10 power minus 4 joules. So it would lose potential energy since it is moving in the same direction in field as the field, and it is a positive charge. Question 4. So in question 4, it's saying the following. Saying, suppose that in a lightning flash the potential difference between a cloud and the ground is 1.0 times 10 power 9, and the quantity of charge transferred is 30 coulombs. So we have two givens. They gave us the potential since it has a unit of V, and they gave us the charge since we see the units of coulombs. So we have delta V, and it is given as 1.0 times 10 power 9 volts, and we have Q, which is given as 30 coulombs. So they're saying, what is the change in the energy of the transfer charge? So when they say this, they mean that they are looking for delta PE. What is delta PE? So we say the following. We say that delta V is equal to delta PE over Q, and we need to find delta PE, so we need to do cross multiplication. So we have delta PE times 1, which is delta PE, is equal to Q times delta V. So change in potential energy is equal to 30 times 1.0 times 10 power 9, which is basically 3 times 10 power 10 joules. This is for part A. For part B, they're saying the following. If all energy is released, could be used to accelerate of a 1,000 kilogram car from rest, what would be its final speed? So they're saying that you release all of this potential energy. Remember that potential energy, it's the energy stored in the object. So if you release all of it, it means that you're changing all of it to kinetic energy. Or if you remember, we know that the change in potential energy as a magnitude is always equal to the change in kinetic energy. So we say that delta KE in this case will be equal to this value, which is 3 times 10 power 10,